This example is dedicated to Coulomb's law. The law states that the force between two charge bodies is in inverse proportion to the distance between these bodies. Here you can see the equation. Q denotes the charge, and R denotes the distance, and epsilon 0 is the dielectric constant. For the configuration on the picture, with the charge of 0.01 nanocoulombs, the force will be 2.247 nanonewtons. Now let's simulate this case in QuickField. I create the new problem. The problem name will be Coulomb's law. The problem type is electrostatic, and I choose the model class axisymmetric. Axisymmetric means that there is the rotational symmetry around the horizontal axis. So this way we can simulate spherical objects. Now you can see the geometry model editor window. You can always open this window by clicking the Edit Geometry button. Now here I should draw the spheres. I'd better switch to the centimeters. Now here in the right bottom corner you can see the coordinates. I switch to the Insert mode and draw the rotational axis. In a geometry model we should add objects in the upper half plane above this axis. Now I should add the sphere. I choose to draw the arc, and this would be one sphere. The sphere is located 10 centimeters to the right, and I draw another sphere and move it 10 centimeters to the left. So the distance between centers of these spheres is 20 centimeters. QuickField cannot simulate unbounded problems, so we should add the boundary. This would be the boundary. Now the geometry model is ready, and here I should assign labels to objects. I switch to Select Objects mode, select the object, and open the Properties dialog. Here I type in the label. This would be the air. This would be the boundary. Let's zoom in. This would be the left sphere. This would be the right sphere. I don't assign any labels to the sphere interior because in my case the spheres are made of conducting materials and the charge is distributed on the sphere's surface. So there will be no electric field inside spheres. Now once I have assigned labels to objects, I should specify physical properties for these labels. I double-click the label name, and here in the dialog I specify the electric permittivity of the air block. Far away from these charged objects, the electric field fades to 0. So at this boundary I can specify zero electric potential. Now for the left sphere I should specify charge. In fact, I only know the charge value. I do not know in advance how the charge is distributed along the surface. To simulate charged conducting sphere, you can do the following. You can specify floating conductor boundary condition, and at some point, for example here, you can add the no charge. So I should create a new label, minus Q, and the charge is minus 0.1 times 10 to the power of 9 coulombs. And the same for the right sphere. I assign floating boundary condition on the sphere surface, and at some point I add the label plus Q, and for this label I specify the positive electric charge, 0.9 nanocoulombs. Now we can build the finite element mesh and run the simulation. Here you can see the equipotential lines. I can zoom in and adjust the picture and switch on, for example, the vectors of electric field strength. And you can see that indeed the electric field strength vectors start at the positive charged body and are going towards the negative charged body. For those who are interested in the electric field strength distribution in the entire area, you can again adjust the field picture and switch on the color map of electric field strength. To calculate the electrical force, I should build the integration contour. I use the contour tool to build the integration contour. You see there is zero electric force acting on the air. So the contour could be of any shape. The only requirement is that the charged body should be placed inside the contour, and the contour should be counterclockwise directed, and it should be closed. Now let's go to the integral calculator and calculate the mechanical force. This is the magnitude of the force. You can see that the force is directed to the right, so indeed these spheres are attracting each other. But you can see there is the discrepancy between the calculated force and these analytical value calculated by the Coulomb's law. The discrepancy is caused by the insufficient mesh quality. You see, when QuickField builds the mesh, the logic is simple. In large object, the mesh size, the finite element mesh size is large. In small object, the finite element mesh size is small. Once we have the results, QuickField can do better. It can automatically adjust the mesh density to get more accurate results. You can use solve and refine option. You see how the mesh was automatically adjusted. Now let's again take a look at the results, and again I will calculate the electric force. Now you see it's much better. We have 2.23 and the law states that it should be 2.24. We can adjust the mesh once more time. I will build the integrational contour and calculate the force. Now you see it's 2.245, and the law states that it should be 2.247. Here is the link where you can find the simulation files on our website and the description of this example. And here at the bottom is the download link.